he will be speaking on equidistribution from the Chinese remainder theorem. Professor Soundarajan.
Thank you very much. So let me,
Professor Soundarajan.
please tell me if this works, if I'm on full screen. Is that, okay, then I don't see my slides, so I have to.
Yes, we can see you.
You can see this? Okay. All right. Do the slides show up as full screen for you, or?
It is. For me, it is full screen.
Okay. Okay. So, I'm going to talk about a recent result that Emmanuel Kowalski and I had been working on, which concerns a kind of equidistribution, generalizing some old work of Hooley on and understanding this as really a consequence of the Chinese remainder theorem. So to set this in context, and I'm not entirely sure what the audience is, so I had a little slide just reminding people of what equidistribution is. If you have a sequence of numbers, let's say in R mod z, so taken mod 1, then we say that the sequence is equidistributed if you pick any interval from alpha to beta and you count how many of these entries land inside the interval from alpha to beta mod 1, and that happens to be the same as, or happens to be asymptotic to the length of the interval times the number of entries that you're looking at. So if this happens in the limit, then we say the sequence is equidistributed. And the fundamental result here is the equidistribution theorem of Weil, which tells you that you can understand this by understanding a related exponential sum. So if you look at the exponential sum e to the 2 pi I k times an, you would like to show that that's trivially equal to n if k is 0. But if k is not equal to 0, we would like to show that this has some cancellation, that it becomes little o of n, can be made smaller than epsilon times n for any epsilon positive. And if we can arrange that, then we would know that the sequence is equidistributed. So this you could use to show that sequences like n times alpha, or a polynomial with at least, say, the leading coefficient being irrational, that these kinds of sequences are equidistributed. And this would be a familiar idea to people who've thought about some problems in analytic number theory. Now, before I actually get to the main theme of my talk, I just wanted to give you a fun example so that if you don't find the rest of this compelling, then you can go and think about this problem, which is just completely unrelated to the rest of the talk. And it's an example that was found by Stefan Steinerberger, and it's purely an empirical fact which we don't have any good explanation for. It concerns a very strange object called the Ulam sequence. So it starts with 1 and 2, and then recursively we define an to be the smallest integer that's the sum of two previous distinct terms in your sequence in a unique way. So the third term becomes 3 because it can be written as 1 plus 2 in a unique way. The next term is 4. It can be written as 1 plus 3 in a unique way. The two numbers are not allowed to be the same, so you can't write it as 2 plus 2. You have to miss 5 because it's both 1 plus 4 and 2 plus 3. And so the next number in the Ulam sequence is 6, and so on. So this sequence, we understand very little about it. We have no idea how this sequence grows. Maybe based on numerics, it seems to have some positive density, but a pretty small density, like 0.07. And a very funny result that was found by Steinerberger, again empirically, is that this seems to have a hidden signal. So if you form the exponential sum with e to the 2 pi I n, some number alpha times an, then it has a signal at this point. Alpha is about 2.57. Okay, so in other words, if you look at cosine of alpha times an, this, if it were equidistributed, this would be equally often positive and equally often negative. but it turns out that this cosine is negative for almost all of the first 10 million Ulam numbers. So this is just a kind of for amusement. It doesn't have anything to do with the rest of my talk, but I would be curious if people have anything more to say on this problem. It's a funny sequence where you get a main contribution on a minor arc rather than on a major arc. So it doesn't have, it doesn't seem to have frequencies that are large on rational numbers, but at this possibly irrational number, it seems to get very large. Okay, so that was by the side. Let me now turn to the main topic of the talk, which starts out with trying to understand roots of polynomials or congruences modulo p. So to give you the most fundamental example, you could look at the simplest quadratic polynomial x squared plus 1. And let's look at the roots of this quadratic polynomial modulo a prime. We know that there are two roots if p is 1 mod 4, and no roots if p is 3 mod 4. So for each prime p that's 1 mod 4, look at the two roots, nu over p and negative nu over p. So let's look at the two roots modulo 1. So I get 2 points for every prime p that's 1 mod 4. So roughly speaking, if I collect all these numbers over all the primes up to x, I get about the number of primes up to x such points, 2 for half the primes. And one of the spectacular results from the 90s is a result of Duke, Friedlander, and Ibanez, which shows that this set is equidistributed modulo 1. So Duke, Friedlander, and Ibanez showed it for all quadratic polynomials where the discriminant is negative, and then Toth did the case where the discriminant of a quadratic polynomial is positive. And in both cases, if you start with an irreducible quadratic polynomial, you look at its roots modulo p, then basically for half the primes you will get two roots, and these roots, if you throw them all together, and after dividing by p, they get equidistributed modulo 1. And we would love to be able to prove a result of this type for any polynomial of higher degree, but this remains an important open problem. Now, but much earlier, there's a result of Hooley, which takes a polynomial of higher degree, where instead of looking at the equidistribution of roots for prime moduli, Hooley looks at a somewhat easier problem, where you just look at the equidistribution of roots modulo any modulus q, not necessarily prime, so potentially composite. And here he proved a very beautiful general result that if you take any irreducible polynomial of degree at least 2, so you look at its roots modulo q, write down the fractions corresponding to those roots, put them together for all q up to x, and then Hooley's theorem is that this set gets equidistributed modulo 1. Okay, and this is the theme of my talk. And what I want to explain is that what's underlying this theorem of Hooley is nothing about the arithmetic of roots of polynomials modulo any number, but instead what's happening is that the mixing is taking place because of the Chinese remainder theorem. In other words, if you take a polynomial and study its roots modulo q, that's the same as studying the roots modulo every prime power divisor of q, and then you put together all the prime power the roots modulo q by using the Chinese remainder theorem on the roots modulo prime powers. So let me try to say the general formalism which will contain the kind of result that Hooley has as well. So the setup is that for every prime power p to the v, I'm going to assume that I'm given a set of residue classes modulo p to the v. And the set of residue classes is denoted by A, PV, and then the number of elements in this set is rho of PV, P to the V. Now, it's possible that for some primes, I give you no residue classes at all, and this function rho of p to the v will then be 0. For example, if you think of the roots of a quadratic congruence m squared plus 1, then on all the primes that are 3 mod 4, I give you no residue classes, and on the primes that are 1 mod 4, I give you 2 residue classes. Now, once you're given this set ap to the v for every prime power p to the v, you construct a set aq for every modulus q, not necessarily a prime power, by using the Chinese remainder theorem. And then the question is, if I look at the sets aq that I get for composite moduli q, do these sets get equidistributed modulo q, at least in some average sense as q varies? Because a typical number up to x will have lots and lots of prime factors. So I might expect that even if for every prime I'm giving you a small number of moduli, a small number of residue classes, then for a typical number q, I might be giving you lots and lots of residue classes, and there's a hope that these might get equidistributed. So that's the question. Is that clear? What the basic question is?
Yes, it is.
So, so let me formalize it a bit more. I'm going to let Q be the set of all moduli Q on which I'm giving you at least one residue class. These are the only moduli that are relevant. And I should need that the number of such moduli that I have up to X should be some reasonably big set. If it is very small, then I may not be able to get a general kind of equidistribution for that set. So I'm going to make the running assumption that for a positive density of primes, the density doesn't have to exist, positive lower density. So for at least a positive density of primes, I'm going to assume that I give you at least one residue class modulo p. And then this is what I'm using to generate residue classes for composite moduli as well. So if I assume this, it'll guarantee that the set of moduli for which I give you at least one residue class modulo q is at least some reasonably big set. It has growth at least x over log x, which is the number of primes, but a little bit more times some power of log x. Okay. Now, the other thing that I need to explain is how I measure equidistribution. And so for every modulus q in your set, I'm just going to put these delta masses at where the residue classes A are in my set AQ, and normalize it by the total number of residue classes. So that gives me a probability measure here, AQ, delta sub q. And then the equidistribution is quantified by looking at the discrepancy. So you look over all arcs on the circle R mod z, and then you look at the arc for which there is the greatest deviation between the number of points on your arc from the expected number, which is just the length of the arc. And so you maximize that object over all possible arcs. And if you can show that that discrepancy is small, at least on average over Q, then it says that these points that we obtained by the Chinese remainder theorem are getting equidistributed at least almost all the time. So that's our goal. And we can only hope to attain this if the set A sub q is actually reasonably big for most moduli q. If AQ has only 1 point or 10 points, let's say, then I'm not going to get equidistribution because the discrepancy is always going to be at least as large as 1/10, for example. If A sub q has only 10 points in it, I can always find an arc of length 1/10, which doesn't contain any points, and that gives me a lower bound of 1/10 for the discrepancy. So one necessary condition that I should impose in order to get equidistribution is that when I give you these residue classes for each prime or each prime power, for many primes, I must give you at least 2 residue classes. So there's ways in which I can fail to get equidistribution. Suppose I give you no residue classes for every prime at all, then I'm giving you no residue classes modulo q. I'm not going to get any equidistribution there. So we had this running assumption that for a positive proportion of the primes, I give you at least one residue class. But again, if I give you only one residue class modulo p, for example, suppose I give you just a residue class 1 mod p for all the primes p, then I would just get the residue class 1 mod q for all composite moduli q, and there can be no equidistribution in this setup. So I must necessarily have at least 2 residue classes in AP for many primes p. And then the theorem is that this is enough. So if I give you a positive density of primes on which I give you at least 1 residue class, and if I give you at least 2 residue classes modulo p for many primes p, then I can show that on average over q, I get equidistribution. And it can be quantified in this way. So p is going to be the sum of the reciprocals of the primes on which I give you at least 2 residue classes. And then I can say that if that quantity p is large, then the average value of the discrepancy is small. It decreases to 0 exponentially in p, like e to the minus p over 6. Which means that if most of the moduli q, with a small number of exceptions, with at most e to the minus p over 12 proportion of exceptions, the discrepancy itself is going to be small. It's going to be smaller than e to the minus p over 12, which means that the sequence of residue classes modulo q is actually equidistributed because the discrepancy is small. And this is the best kind of result that you could hope for, because just by probability consideration. Sure, go ahead.
So the number of primes for which you are assuming that the number of solution is at least 2 is for all of them the positive set, or only for infinitely many of them?
So I'm only assuming that I'm not. So I'm assuming this condition here. I don't know. I'm not sure I can point. Yeah. So it's the line about the definition of P, of capital P. So it's only assuming that that the sum of the reciprocals of the primes on which I give you 2 residue classes, that sum is large. So for example, if on a positive proportion of primes I give you at least 2 residue classes, this will follow.
Yeah.
But I need to assume only something very mild on that.
Okay, thank you.
Does that answer your question?
Yes, thank you.
Okay. So now, in general, you would expect that that there are lots of moduli Q on which I'm not divisible by a prime for which rho p is at least 2. So on this proportion e to the minus p q of x, I might expect that that I give you only 1 residue class modulo q for this set of moduli q. And so apart from this this 6 in the theorem, the 1/6 in the theorem, apart from that constant, the result is basically best possible. Okay. Now, that's a generalization of Hooley's theorem, because if you pick any irreducible polynomial of degree at least 2, then by the Tributary density theorem, you would know that the polynomial will split completely, and so it will have d roots. Rho of p will be d for a positive density of primes. At least for a density of like 1 over d factorial, you will get complete splitting of that polynomial. And then the condition of the theorem will apply, because for a positive density of primes, I get rho of p is at least 2. So the sum of the reciprocals of the primes on that positive density set will be guaranteed to be large, and we have equidistribution. Now, the way in which I've formulated the theorem is actually slightly different from what Hooley did. So what we are doing in this theorem is that we have these sets modulo q that we get by the Chinese remainder theorem. We take all of those sets divided by the number of elements in that set. So that's a probability measure here, and we are saying that on average over q, that these probability measures get equidistributed. What Hooley does is a little bit slightly different. He takes all the roots modulo q And then he takes the set of that, he takes that set and averages it over all the moduli Q as well, and then takes divides it by the total number of points. So you can see it's slightly different here. We are averaging a bunch of probability measures. Hooley puts all those points together and then forms a probability measure. So there are two different ways of formulating the problem. Neither of them is in general equivalent to the other. But the way in which we've formulated the problem allows for this very general result, but Hooley's formulation, in a funny way, does not. So there are counterexamples in general to Hooley's formulation. If you take very big sets for every prime p, if I give you like p over log p residue classes for every prime p, then the primes actually dominate. So if you try to put them all together for all moduli q, the primes will be a positive proportion of all the numbers that you get. And then on the primes, you can choose basically a random set. You can choose the set to be the first p over log p residue classes, and then you will not get equidistribution. So Hooley's theorem does not extend in this generality. But in our case, each modulus, you have just a probability measure, so the primes are not allowed to dominate in this case. The primes will still be only a zero density of all the moduli Q that are allowed, and you can still prove equidistribution in that case. So that's the theorem that I'll explain a little bit about at the end. At the moment, I'll try to tell you a little bit about how we generalize this theorem to higher dimensions, and then also we generalized it to results where you can restrict your attention to not all composite moduli Q, but just moduli with a given number of prime factors. Okay, so let me first tell you what the setup is in higher dimensions. I've been talking so far about the one-dimensional case where I give you a set of residue classes just modulo p. So now I want to give you a set of residue classes in z mod p z to the n, or z mod p to the v z to the n for some prime power. And again, I'm giving you some number of residue classes, a tuple of n tuple of residue classes for each prime power. And then I extend these to a tuple of residue classes mod q by the Chinese remainder theorem. So in each coordinate, you use the Chinese remainder theorem to construct your new set. So once again, we have a multiplicative function rho of q telling me how many residue classes in z mod q z to the n that I have, built out of the residue classes modulo prime powers. I'm going to make the same assumption as before, that on a positive density of residue classes, I give you at least one n-tuple modulo p. So this set q of x is again at least of size x over log x times log x to the alpha for some power alpha positive. And then we would like to understand the equidistribution of these sets AQ in R mod z to the n. So once again, I form this probability measure, take every n tuple of residue classes divided by q, I get a point in R mod z to the n, put them all together and form a probability measure. And what does it mean for these to be equidistributed? Again, we can look at the equidistribution through the box discrepancy. So take any box in R mod z to the n. Let's say all the sides are parallel to the axes. And then count how many points land inside this box, subtract it from it the volume of the box, and then you would like to take the maximum deviation of the expected number of points inside your box from the volume of the box. You take the maximum of that deviation over all possible boxes. So that's the discrepancy. And once again, we would like to show that this discrepancy is small, at least for a typical modulus Q, in which I give you at least 1 point. Now, to formulate the problem here, there are, in the one-dimensional case, the only obstruction to uniformity was that I could be giving you very few points modulo q for most moduli q. So as soon as I guaranteed that I was giving you 2 primes in every, for many residue classes, I could guarantee equidistribution. So here the problem is a little bit more tricky. It could happen that suppose I gave you for every prime, I gave you lots of points, but these points all lie in some hyperplane. So suppose, for example, all the points that I give you in z mod pz to the n have the property that their coordinates all add up to, let's say, 1 mod p. If I do that, and then I build points using the Chinese remainder theorem, then all the points that I give you modulo q will also land inside the same hyperplane, and you can't expect to get any equidistribution, even though I might be giving you more and more points modulo q. So in other words, I must find some way in which I can guarantee that the points that I give you modulo q don't all concentrate on some subtorus of R mod z to the n, or some translate of a subtorus of R mod z to the n. So in the one-dimensional case, the translations of the subgroups of z mod pz, well, there's just the one subgroup, just the point at the origin 0, and then I can translate it around. So this just amounts to be saying that I don't just concentrate on one point in AP for many, many primes p, and that was the assumption that we had. So now we want to make some assumption that if I take any hyperplane, any affine hyperplane in z mod pz to the n, and I look at the maximum number of points that I get inside this hyperplane. So I take AP, I intersect it with any affine hyperplane, and then I would like to know that this lambda p is not as big as the total number of points in my set AP, which is rho of p. So let me formulate this condition. So I look at the maximum number of points inside the hyperplane, and I would like, and which is always bounded by the total number of points in my set AP that I have. And what I need to guarantee is that sometimes I have more points in my set AP than just the maximum number of points that land inside a hyperplane. So in the one-dimensional case, lambda p is just 1. The hyperplanes are just points. So I just don't want to land on one point. So the maximum number of points in my set that can land on a point is just 1. And so I needed to know that rho of p is at least 2 for many primes p in order to get equidistribution. And here, if you like, you can think of in n dimensions, the generic condition would be that I should have at least n plus 1 points, because any n points can be put inside some affine hyperplane. But if I give you n plus 1 generic points, then they will not lie in any fixed hyperplane. Okay. So here is a precise statement of what we can prove. So if in n dimensions you form sets modulo q, z mod qz to the n by using the Chinese remainder theorem, then if you average the discrepancy over all these moduli q, then you get a bound on this average discrepancy, which goes to 0, provided this object here tends to 0. So what is this object here? This sum over primes. It's basically saying that so lambda of p is the number of points that lie inside a hyperplane, the maximum number of points inside a hyperplane. Rho of p is the total number of points. So imagine that for a lot of primes, only, let's say, half of the points that I'm giving you modulo p lie inside a hyperplane. If that's true, then this fraction will be at least a half. And then I'm saying that the sum of the reciprocals of the primes on which that happens is reasonably big. So if that quantity is big, then I get equidistribution. So in the one-dimensional case, lambda p is 1. And so if rho of p is at least 2, then this is at least half. And that's the theorem that we proved, that I explained before. That you get equidistribution provided for lots of primes p, rho of p is at least 2. And in higher dimension, it says that if you can escape any given hyperplane, then you get equidistribution. Now, any questions?
Is that why this 3 shows up? Is there a explanation for that 3, 1 over 3?
No, this is just some constant that we have. I think in general, it'll be, so the constants we haven't optimized, so potentially there could be a better constant there.
Yeah.
But you can't get a better result than just some constant like 1 there, because you can, you might still have, just by random chance, that there would be lots of moduli q for which you're not divisible by a prime for which lambda p is not the same as rho p, and then apart from this constant 1/3, you wouldn't get a better result.
Thank you.
Okay. So the other variant that we can establish is you can restrict attention to integers with a given number of prime factors. So most integers would have about log x prime factors, and so they would have lots and lots of primes p, maybe with AP at least 2 in the one-dimensional case, or something bigger than lambda of p that divide it. But in fact, you can do a little bit better. You can just restrict attention to numbers with k prime factors. So long as this k is reasonably large, we can guarantee that you get equidistribution even on this set. So let me explain what it means. So let's say in the n-dimensional case, suppose I tell you that that most of the time you're going to avoid any fixed hyperplane. So that's this object here. Let's say for a positive proportion of primes, I avoid being inside of any given hyperplane. Like at least say, only half of my points can lie inside a given hyperplane for a positive proportion, let's say. If I assume that, then I can say that as soon as k gets large enough in terms of delta, so in other words, it just needs to go to infinity. If the number of prime factors in your set just needs to go to infinity, if I can arrange that, then I get equidistribution on numbers with k prime factors. Okay, so let's say there's if you think of the one-dimensional case, and if you think of roots of a polynomial, there'll be a positive density of primes on which you get equidistribution in Huli's theorem by the Tributary density theorem. So in this case, it's telling you that if the number of prime factors tends to infinity, then you're likely to get on almost all of those numbers, you're likely to get equidistribution of the roots of a polynomial congruence. So that's one strengthening of Huli's theorem in this case. So this equidistribution is being measured by e to the minus k times delta. So if delta is some number and then k just tends off to infinity, then this parameter here just goes to 0, telling you that most moduli in that set get equidistributed. So there's a question in chat about how large k should be in terms of delta, and that's what you can see here, right? So if k is growing like something large in terms of 1 over delta, then you get this equidistribution in some qualitative sense. Okay. If you make a stronger assumption that that you're really given many more points in your set than can land inside a hyperplane, or in other words, in the one-dimensional case, you just assume that rho p is actually very large for every prime p on which it's not 0, then you start getting equidistribution even when k is 2. So this is some small parameter delta, and then it's delta to the k minus 1 divided by some power 10. This 10 is just an artifact of the proof. Maybe it could be made larger. So the 1/10 could be made larger. So on primes, you can't hope to say anything in general, because I could give you the first, log p raised to classes modulo p for every prime p. This is not going to have any kind of equidistribution. But if you take that example, and if you look even at numbers with just 2 prime factors, on average, you will start seeing equidistribution on numbers with 2 prime factors. So here's that spelled out. If I just give you log p residue classes for every prime p, then if you look at, no matter what these log p residue classes are, if I look at numbers with 2 prime factors, I will get equidistribution for almost all such numbers. Okay, let me now give you some applications of these results, and then I will give you a small indication of how the proofs run. So the nicest applications are when you have a set that's defined globally and doesn't make any reference to the Chinese remainder theorem, and then the Chinese remainder theorem, is implicit in that construction. So polynomials are a nice example of that, because I can talk about the roots of a polynomial modulo q, and the fact that they come from the Chinese remainder theorem is follows, but it doesn't appear when we initially consider the problem. You can look at an n-dimensional version of the polynomial. So suppose I give you a polynomial of degree d, I can look, for example, at the following. Look at the roots of the polynomial modulo p, and then look at the following d minus 1 tuple, a squared, a cubed, all the way up to a to the d minus 1. And then we can ask if that gets equidistributed modulo p in all d minus 1 coordinates. If you look at this this particular d minus 1 tuple, so it's like a curve x squared, x cubed up to x to the d minus 1. So that's a curve of degree d minus 1, and it can intersect any hyperplane in at most d minus 1 points. So in this case, this lambda of p, which is the maximum number of points in which my set AP can intersect the affine hyperplane, is always bounded by d minus 1. Now, the Tributary density theorem tells me that for a positive proportion of primes, f will have d solutions modulo p. So rho of p will be d for a positive proportion of primes, and lambda of p will be at most d minus 1 for every prime p. So therefore, this 1 minus lambda of p divided by rho p in my theorem can be made larger than some constant, can be made larger than 1 over d for a positive proportion of primes, which means that the theorem will apply, and it will tell you that these d minus 1 tuple of residue classes get equidistributed for almost all moduli q. So that's the generalization of Hooley's theorem. Now, the only theorem in which we can prove Hooley's case for primes is in the case d equals 2, where there's no gain here. You can only consider the root modulo p. So that's the only theorem in which you can prove anything on primes. But Khrushchevsky recently conjectured that this is true for any polynomial of degree at least 2, and then that this d minus 1 tuple gets equidistributed. This is a conjecture of Khrushchevsky if you average over the prime moduli as well. As I said, nothing is known here, because the only situation where we know something for prime moduli is in the case of degree 2, the Dukefeld and Riemannians. So, and what I've just explained is an analog of Khrushchevsky's conjecture for composite moduli Q, where you get this analog just by the Chinese remainder theorem. There are a number of extensions of this flavor that you can form for polynomials. You can restrict to the moduli having a fixed number of prime factors. You can restrict those prime factors to lie in a certain set. For example, you could ask for all those prime factors to be 1 mod 4, or be represented by some other binary quadratic form, all kinds of variants of that type. You can restrict the roots of your polynomial themselves to be roots of some other polynomial. So it's like composing 2 polynomials and asking for roots of that. You could ask, for example, that the roots themselves are quadratic residues modulo p. Another variant is that there's a result of Krizan and Pollack, who looked at Hooley's theorem and showed that the smallest root modulo q is often below q times some small power of log q, q divided by some small power of log q. This follows from our result because we actually give you a bound on the discrepancy you get a bound on the discrepancy, saving a small power of log q. So it just says that if you look at a very small initial interval, you will get points inside that initial interval as well. In fact, you will get points inside any interval of measure log q to the minus delta for almost all moduli q. Heath Brown pointed out to us an application where you can look at the roots of an irreducible form in, let's say, degree at least 2, and then you can ask for the equidistribution of these roots in z mod pz or z mod qz squared, and again this will be guaranteed by the result that we have, that I stated. So one other kind of funny example is that you could take two elliptic curves. I just gave you two curves here. You can play around and find all kinds of examples, and then you can say that you can try to look at the points of intersections of these in z mod pz squared, and then try to show that the process that you get by doing this for z mod qz squared, they will get equidistributed for almost all moduli q. And the reason is that in general, you'll get a bunch of points, and all you have to check is that they don't all land inside some line. Now, in any line, you can only get 3 points because these are cubic curves, and so only 3 points can land on any line. And once you have a set of moduli p of prime moduli for which the intersection points of these two curves, you get more than 3 points. If you can guarantee that for a positive proportion of primes, then it will follow that if you look at the points modulo q for a generic q, they will get equidistributed. And so if you intersect two of these curves, apart from points points at infinity, you should find 9 points for many primes p, and if you account for the points at infinity, you can make this larger than 3 for a positive density of primes. Now, there is one other class of examples, and these are a very funny kind of object called pseudo polynomials. A polynomial has the property that if you look at f of n modulo p, it's determined by n modulo p. So in other words, if I take f of a minus f of b, it's always a multiple of a minus b. But there are other objects which are not polynomials, but still satisfy the property that a minus b always divides f of a minus f of b. In fact, there's an uncountable number of these examples, and these are called pseudo polynomials. So roughly speaking, a pseudo polynomial can be expanded in terms of binomial coefficients. You can write an expression for it in terms of a0 plus a1 times n choose 1 plus a2 times n choose 2 plus a3 times n choose 3 and so on. Now it's an infinite expansion, and the point would be that if ak is a multiple of the LCM of all the primes below k, LCM of all the numbers below k, then you can guarantee that this satisfies the pseudo polynomial constraint. So that's the theorem of Richard Hall and also of Ruja at the same time. So here are some funny examples. You could look at the floor of e times n factorial that happens to be a pseudo polynomial. You could also take n factorial divided by e, which is roughly the number of derangements in the symmetric group Sn. That also happens to be a pseudo polynomial. You could then ask about questions like, take the primes that divide as the values of a pseudo polynomial, and then ask for the equidistribution of the roots of these pseudo polynomials. This is, of course, a very bizarre kind of problem, and nothing can be said about it. For example, it would be nice to say that if you look at the number of derangements, maybe you can say something about what are the primes that divide the number of derangements. We can't quite do that, but our work will apply to this funny example where you can look at the number of permutations in Sn that have exactly one fixed point. This turns out to be also a pseudo polynomial, but here we can guarantee that for a positive proportion of primes, you get at least, actually for every prime, you can just construct that there are two roots, modulo p, and then the Chinese remainder theorem will take over, and you will get equidistribution of the roots of this pseudo polynomial modulo q for every modulus q. Now, there are way too many pseudo polynomials, so there's no analog of Cooley's theorem for all pseudo polynomials. This was shown to me by my student Vivian Cooperberg. She has a nice small note on the archive which constructs pseudo polynomials for which you don't get equidistribution. But maybe for natural classes of pseudo polynomials like this e times n factorial or derangements, you do get equidistribution. But this is very far afield, and I don't really have a good idea about, well, first of all, whether these problems for pseudo polynomials are interesting or how one would go about thinking about them. There's clearly no such thing like the Tributary density theorem that we know that talks about roots of these pseudo polynomials modulo p. So I have a few minutes in which to tell you something about the idea of the proof, a very brief sketch of the proof. Let me just say, where the key input is coming from. Some of these ideas go back into Cooley. So if you, let's say in n dimensions, if I want to prove this equidistribution, I'm looking at a Weil sum. So I have these points x in my set AQ, and I want to look at the equidistribution of this exponential sum of h dot product x. And I would like to know that this guy, on average, these normalized Weil sums on average over all moduli Q exhibit some cancellation, that they are smaller than just summing one in that set. What's behind this cancellation in the Weil sums is that if Q is a composite modulus, there is a kind of twisted multiplicativity of these Weil sums. So they're not multiplicative. If they were multiplicative, it would not be so possible to prove anything, but there's a twisted multiplicativity that comes from the Chinese remainder theorem. So if Q is Q1 times Q2, then you can write this 1 over Q as Q2 bar over Q1 plus Q1 bar over Q2 modulo 1. So Q2 bar is the inverse of Q2 modulo Q1. Q1 bar is the inverse of Q1 modulo Q2. So if you use this, this is the statement of the Chinese remainder theorem. Chinese remainder theorem is the definition of the Weil sums. The Weil sums will satisfy a twisted multiplicativity. The Weil sum modulo Q1, Q2 will be the Weil sum modulo Q2 with this Q1 bar here, and then a Q1 with the Q2 bar here. They factor in this nice way. So now if you fix Q2 and vary over Q1, then this Q1 bar gets equidistributed modulo Q2, and that's kind of mixing around these Weil sums, the parameter in this Weil sums a bit. Okay? So the idea is to factor a modulus Q. A general modulus will have lots of prime factors. I'm going to factor one of these moduli into two parts, and the smooth part S. So I have some parameter Z, which is some very small power of X, maybe like X to the 1 over log X. So every modulus will have lots of prime factors, most of them. So the smooth part will be pretty big, and the rough part will be, but not too big, say smaller than X to the 1/3 or so. And then the rough part will have a small number of prime factors, all larger than Z. And if I use this twisted multiplicativity, I can now separate the two parameters R and S, and I have a Weil sum modulo R and a Weil sum modulo S. So a Weil sum here modulo R and a Weil sum modulo S. On the rough part, think of R as being like a prime or a product of a small number of primes. On the rough part, I can say nothing, so I'm just going to put a trivial estimate on the Weil sum here, just bounded by 1. It's a normalized Weil sum bounded by 1. And then I want to use the fact that the sieve, just the simple, Brun sieve or any kind of sieve in progressions, will tell you that if I look at the number of rough numbers in a given progression modulo S, it's the number of these is always bounded by the expected number. So I kind of fix S and then look at the sum over R and say that all the possible residue classes that R can take modulo S more or less appear roughly equally often. So that gives me this averaging in R bar modulo S. So instead of just having a fixed Weil sum modulo S, I get to average my Weil sums modulo S by this parameter a modulo s. Okay, this is where the Chinese remainder theorem has kicked in, and this is the source of the cancellation. So now, now instead of having just one while sum modulo s, I have this average over the parameter a. So what am I saving? The trivial bound on this is 1, because each of these while sums is bounded by 1. But I can do better by Cauchy-Schwarz. So if I use Cauchy-Schwarz on the sum over a and expand out what that's giving me, that's basically giving me by Parseval, it's giving me the number of points inside my set AS, which have the same dot product when I multiply x1 and x1. When I dot it by h, I get the same remainder modulo s. So in other words, if I fix x1, and so I fix the dot product of h with x1, then the number of x2 that I'm counting is really the number of points in my set that land inside the hyperplane, having the dot product with h being the same as a. So this is where my constraint comes in. I'm assuming that the maximum number of points in my set AS that land inside any hyperplane is bounded by this parameter lambda of s. So if I sum over x1 here, if I fix x1, the number of choices for x2 is no more than lambda of s. And then the number of choices for x1 is just rho of s, the total number of points that I give you inside my set. So here's where I've saved something. Instead of putting a trivial bound of 1, I get to save a bound of lambda s divided by rho s. So if for many primes p, I get rho of s is bigger than lambda of s, typically, let's say by a factor of 2, then if s is a smooth number which has a lot of such prime factors p, then I'm saving something small here on for the average of these file sums. Okay, so if you think of the one-dimensional situation, lambda of s would just be 1. So what I've saved here is that on average over these while sums, instead of putting in a trivial bound of 1 here, I get to put a bound of 1 over rho of s, so to speak. And so if rho of p is bigger than 2 for many primes p, you can see that I start saving progressively more and more for a smooth modulus s. So that's kind of a very quick overview of the proof. Do I have a full hour or do I just have 50 minutes?
No, you can take more time if you want.
Okay, so just to give you one last application, I won't say more. You can use this circle of ideas to say something about averages of while sums, even for say polynomials, while sums attached to polynomials, to composite moduli. The way bound for these while sums would say that on a prime p, if I take a polynomial of degree d, these are bounded by d minus 1. So this would be bounded by like the divisor function, the d minus 1th divisor function for a general modulus q. But you can actually, on average over q, you can do better. And this is the kind of argument which was pioneered first by Hooley and then studied also by Fouvry and Michel. And the only new input here in this result is that we can say that for very generally for a polynomial f, so long as this polynomial f is indecomposable, we can prove a bound on this mean square where you don't get these extra powers of log that you would get from just putting in the way bound. In fact, you get no powers of log at all, and maybe you can even remove this powers of log in general. And indecomposable means that f should not be the composition of two polynomials g and h of smaller degree. Okay? So in particular, if your polynomial has prime degree, and if you take the while sums of your polynomial modulo q, then in mean square, you get to save something over the trivial bound that you would get from the way bound. So Fouvry and Michel had established results of this type using results of CADS on equidistribution of roots of these polynomials. The fact that that these while sums behave like like traces of large random matrices coming from certain groups. So this is a little softer, and we don't need any assumptions on what F is, apart from this assumption, which is easier to check than the kind of assumptions in Fouvry and Michel. And here, let me just give you one beautiful result here, which is a result of Fried that goes into this proof. And to state Fried's result, it answers a question of Schur. Schur asked, if you take a polynomial f with integer coefficients, when can it happen that for infinitely many primes, the polynomial f modulo p is actually an bijection? So the polynomial f modulo p takes all the possible values modulo p. The set of values of a polynomial modulo p is the whole set of residue classes modulo p. When can that happen? So one way in which it can happen is that if your polynomial is like x to the n, and then, you know, for let's say if your polynomial is x cubed, then for every prime that's 2 mod 3, it is going to represent all the residue classes modulo p. But basically, you can classify when this happens, apart from polynomials like x to the d and some polynomials coming from Chebyshev polynomials. This basically doesn't happen. And this is the kind of result that was proved by Fried. This is a slightly more precise version of Fried's result on answering this question of Schur. That underlies, along with this idea of the Chinese remainder theorem giving you twisted multiplicativity, underlies the theorem that I explained, that I stated in the previous slide. Okay, that's everything I wanted to say. Thank you very much.
Thank you very much for the beautiful talk. Is there any questions from the audience? Are there any questions from the audience? Yes, please.
Yeah.
Let's go ahead.
Hello, sir. Thank you for the beautiful talk. Sir, I was just wondering, in the result which estimates the average of the discrepancies of delta Q over Q and QX, like this is from the earlier part, like by some sum, by an exponent of negative 1/3 times sum of 1 minus P over rho.
Do you want it in the one-dimensional case or the
one-dimensional case?
Yeah.
So,
Can you see the slide?
no,
Yeah.
Slightly later. Like the term on the right is exponent of negative 1/3 times sum of 1 minus lambda p over rho p.
Okay, so that's the n-dimensional case, right?
Oh, okay, sorry. Sorry.
So this one,
Right. So I was just wondering, could it somehow be related to the effective version of Wersing's theorem due to Hall and Tenenbaum? Like, is it somehow related to that?
I see what you mean. So, I mean, not per se, because that theorem is about mean values of a real multiplicative function. Let's say it takes values between -1 and 1. I think that's what you're thinking of, right?
Right. Could that be generalized? Maybe, I don't know. I was just wondering.
This one is a little bit different in the sense that this discrepancy delta Q is not a multiplicative function, right? I mean, the objects are constructed out of multiplicative functions, but this discrepancy for a modulus Q is nothing multiplicative. Yeah.
Right.
So, but of course, you know, many of the ideas in the proof involve ideas involving mean values of multiplicative functions and so on. But there's no direct connection between the result that you mentioned and.
So it borrows some ideas from there.
It certainly borrows ideas from not from that theorem, which has to do with, say, Hallas's theorem on mean values of multiplicative functions, but there are other ideas from mean values of multiplicative functions that I use here, but not related to Hallas's theorem.
I see. All right. Thank you. Thank you.
So is there any more question from the audience? If there are no more questions from the audience, let us thank the speaker for this beautiful talk. Have more talks from you next semester as well. Thank you. And can you have your slides? Is it possible to have your slides so that you can present?
I'll email you the slides. Yeah.
Thank you very much. Thank you.